Yeah, I've got quite a few integrations to look through, if that's
Yeah,
all
good.
right today.
Fine. Yeah. Um,
Cool.
so what kind?
There's a few in this section. So there's a few which they want you done by
Yeah.
um,
No, no, no. I don't.
reverse.
Sorry.
And
Yeah, that's cool. But what kind is this?
oh, what kind is this? Reverse chain rule.
Yeah.
Is that what you mean?
Yeah.
Yeah,
Yeah.
yeah.
So inner and outer.
Six. The let me think. The
And then don't forget this expression here, because that says the integral of that. So we should be able to pass the expression itself in this form. So the inner function is, and the outer function is what?
the the inner function is 6 sine 3x, isn't it?
No, careful. That won't work out. Will it?
Um, well, what does? Oh yeah, no, okay. It will be yeah because minus cos differentiates the sine.
Well, that's right. When you get a reverse chain rule as a fraction like that with the numerator, it's tempting to look at the numerator as being the main business, but the numerator is just the derivative of the inner function, we hope,
Yeah,
or like it. It might not be exactly, you see. So there might be adjustments to be made.
yeah.
But
Um,
basically, you're trying to fit the integrand, what you're starting with, into this format.
mm.
This, as I say, yeah. Anyway, um,
Oh yeah, of course. Because when you differentiate minus cos 3x,
yeah,
you're gonna get three
yeah. Your
cos 3.
your instinct is to think, oh well, surely I can't be putting all of that in there. That's too complicated. But no,
Mm,
because when you differentiate it, the one disappears, and all you've got is what? What's the
yeah,
derivative of one minus cos 3x?
isn't it 3 cos 3x?
What the derivative of cos is cos. You're right about the three because
Oh
of
no, sorry, 3 sine
so
3x.
three positive sign because it's minus cos, yeah?
Yeah,
Cos would be minus sine, but minus cos is sine. And you're right about the 3 coming out because of an additional chain rule inside there.
yeah.
So we look at that, we think, what else have we got to fill in, as it were? The equal sign isn't true yet, is it?
We need no. Um, so we let's see. 1 minus cos 3x. Well, that is to the power of -1.
Good. So that's the outer function, which basically tells you the outer function up here must be
The outer function there must be ln.
good, natural log. Now we can test, see if it's all working, if the equal sign is ready. Well, in fact,
Um,
we're
it
already,
still need
yeah,
how we've still got 3 sine 3x, and we need 6 sine 3x.
yes, quite.
Um, so we need to times that side by 2,
Yeah, and therefore,
and therefore times the top by 2.
yeah, plus C.
But
Or,
how come?
or rather, yeah, sorry, say again.
Oh, okay. So, but because we've got this to the power of 1, -1. Sorry,
Yeah,
we'd only multiply the 2 through the top. See what I mean? So it becomes 6. So it becomes 6 sine 3x over 1
Oh,
minus
that's
cos
right.
3x.
I mean, when you simplify the
Yeah.
bottom, you have got precisely this, haven't you? The power of
Yeah.
-1 is putting that underneath. 2 times 3 is
Yeah.
it's all good. And so we just need the limits from there to there. Pi over 9, is it? Oh, still, that'll probably come out in the wash. So, yes, because we're multiplying by 3. So we have to think about cos of 2/3 pi. What time on the clock is 2/3 pi?
2/3 pi is 1:11.
11 o'clock, good. And cos is what feature of the 11 o'clock mark? Horizontal or vertical?
Was the vertical.
Bad luck. X, your x and y coordinates on the unit circle are cos and sine respectively, aren't they?
Yeah.
So cos,
So cos
is
is
the
the x.
horizontal aspect of 11 o'clock. And what's the horizontal aspect of 11 o'clock?
Sine.
Sorry?
No, horizontal cos.
Right.
Horizontal is
and 11
cos.
o'clock in particular, what's the horizontal coordinate of 11 o'clock?
It would be 2. It would be like out of 1.
It's a unit circle, yes, assume. Yeah.
2/3.
We'll just look at it quickly. Hang on. K.
Oh no, the horizontal. I'm being stupid. 1/3.
Not a third. 11 o'clock. There's the center. And we're asking what's the horizontal coordinate of 11 o'clock? Well, you've got this nice.
Yeah, I thought that was 2 and 1. Isn't it?
Yes, right. Well, that's right. That is half of 1. The ratio is 2 to 1. 2 there, 1 there. Or 1 there and a half there.
Right.
Equilateral triangle. 2/3 pi, which is 11 o'clock. Cos, because the horizontal aspect, the horizontal coordinate axis is cos. -1 there because it's a unit circle. This distance is a half. So that coordinate is -1/2.
Oh, okay, yeah. All right, yeah. I see what you mean now. For some reason, I was thinking, how long is it?
True, yeah. All of these things are relevant and potentially confusing. Yeah, distracting, whatever. Whoa, and now, therefore, using that now. So we multiply by 3 to get 2/3 pi, which is 11 o'clock. Cos of that is, we've just agreed.
-1/2.
Oh, careful. The length of that is a half, but we're taking these as coordinates. So the cos coordinate is -1/2. So the cosine of 2/3 pi is -1/2. -1/2, not the magnitude, which is a half there.
Yeah.
It's probably confusing to have that half there.
Cos -1/2.
Cos of that angle is minus a half, yes.
Right, okay. Okay.
Okay, so using that here, what do we get?
Cos minus cos 3/2.
That's coming out garbled. I think you're thinking some of the right things there. It's coming out garbled. It might not, you might be writing it correctly. I don't know. Have another go telling me, I mean, 3x is 2 pi over 3, isn't it?
Yeah.
So cos 3
Wait, what? Yeah.
is cos of 2 pi over 3,
Oh,
which is cos of 11 o'clock. So you've got to say 1 minus
yeah.
cos of 11 o'clock. And you've just clarified
Yeah.
cos of 11 o'clock as what value? Remind me what cos of 11
Minus a half.
minus a half. So really, this is saying natural log of 1 minus what?
Co 1 minus 3/2.
1 minus 3 over 2.
1 minus cos not 3 times a half. 3 times minus half.
Right.
Cos 3/2x.
No. Step. Cos of 3x, right, equals cos of 2 pi over 3, which equals horizontal aspect of 11 o'clock, which equals what?
Minus half.
Good. So 1 minus cos of 3x equals?
Oh, 3/2.
Yes. Now you did say 3 over 2, but you said cos 3 over 2, which is why I said I thought it was getting garbled.
Yeah. Yeah, I was confused.
I think your 3 over 2 must have come from the right place-ish. But it's log 3 over 2, basically, isn't it?
Yeah.
And it's twice that. So log 2 log of 3 over 2.
How
Minus.
come you replace? Oh no, no, I understand. Okay.
Minus 2 log of what?
Minus 2 log. What is it now? Pi over 9. So.
Yeah.
Um.
So this time cos 3x is going to become cos of what angle?
Cos 3x will become just pi over 3.
Yes, which is what time on the clock?
Which is 1 o'clock.
Which is what cos?
Which is a half.
Which is this time positive a half. So
yeah,
we're taking the natural log of 1 minus what?
1 minus a half, so not just a half.
Just a half.
A half.
Right.
Yeah.
And then we just need to simplify the logs there, which we can, because we've definitely got, well, we could just say it's 2 log of, no, we couldn't. Hang on a minute. Yes, we could. Yeah. I'm thinking that.
Yeah. Okay, so that would be 2 ln 6 over 2. So 3 over 2.
Yeah, 2's cancel basically.
Yeah. Cool. Should we do
so
the next one?
that's just backwards chain rule. Good. Yep.
C. I'm happy to.
Sure.
Good.
Yeah, definitely just by inspection. Whoops. Pass it.
X squared minus 1 in that left hand side.
Yes. In what?
Um,
In what part of it?
in the left part, the middle.
The inner function.
Yeah.
I agree. Good.
And then X, and then X. Oh no. Yeah, and then
Yeah,
return
maybe.
minus 1.
We have to sort of stay a bit vague about the rest of it until we've sorted out what must be in here.
Yeah.
What must be in here?
X.
Well,
No,
no, we'd like it to be X, but it might not be that clear cut. What must be in here is the derivative of the inner function, which is the same up there as it is down below. So this must be exactly what?
this must be 2x.
So now the outer functions are what and what?
The outer functions are on the bottom minus 1 and on the top ln.
As long as you mean power minus 1, yes, good, which you do, clearly.
Yeah. And then what we've got to do is divide by 2
Right?
on the top and bottom.
Yes. In other words, we never say divided,
In other
we
words,
just say
times
times.
by half. Yeah.
Equals?
Equals, what numbers are we putting in? 7. So 7 squared minus 1 is 40, half ln 48.
Good.
And minus half ln 15.
Great. Simplifying to?
Simplifying to half ln 48 over 15.
Which simplifies to 48 over 15. They both divide by 3.
That would be 48 over 3. 16
Over
5.
Good. Now, do you see how that simplifies also? Because you could write it as natural log of what?
You could write that as natural log.
Of course, it doesn't simplify all that much, actually. Perhaps it's best left like that, actually.
What were you thinking of saying?
This, somehow ignoring the fact that 5 doesn't have a nice square root. Although 16 obviously does. But that, then I'd have to put a root 5 there, which isn't particularly nice. So this, in a way, looks neater than that. But you see what I was thinking, half thinking.
Yeah.
Okay, the multiple of a log can always go and be a power inside the log.
So you could just scroll up a little bit, just so I can see how we. Yeah. Okay. Log ln. Oh, I see what you mean. You've done that. Okay. Right. Okay. Good.
D.
Could we just go straight to 4? Do you think?
Sure, yeah. So you want to kind of ignore that and just say, okay, well, when we've done this, we'll solve it for the value of, what is it? K. In other words, when we've done this in terms of K, we'll use that to settle K. But ignore that for now and just do all of this in terms of K. Where K is an unknown, what do we say? K is an unknown.
Integer.
Unknown what?
Integer.
Constant. Possibly an integer,
Constant.
possibly not an integer. May be rational or real, but thinking of it as a constant rather than a variable. If it was a variable, things would be much more complicated. So it's just an unknown constant, like 3 or 5, whatever. So how shall we pass it and how shall we tackle it probably?
Okay, well, e to the x to the 3 is probably going to be in our function.
Oh yeah.
Well,
yeah, I was thinking by parts, but of course you're quite right. Yes, if we take oh, what's the inner function? Sorry. So yeah, I think you're righter than I was, but careful. What's the inner and outer?
So inner is e.
No, not if you mean not unless you mean, not unless you're thinking composite and you really mean outer of the composite. E is the outer.
Oh.
What you mean.
Okay, and then the inner is x to the 3.
Yeah. In which case, the inner derivative is.
The inner derivative is kx
Well,
squared.
Only if k is equal to what?
Only if k.
See, I don't know why.
To...
Again, remember when we were here, or was it here? Well, it was here, and you said, "Oh, I think that's x," but that was wishful thinking because you wanted that to be exactly x. The inner derivative will be what it has to be. So again, you're trying to bring the k into it as wishful thinking, but actually the inner derivative must. That's mechanical. That's automatic. The inner derivative is just what it is, which is what?
Which would be
because the inner is going to be the same up here as it is down there. So the inner derivatives just must be
3x squared.
yes. Now, where does the k come into it? Well, we don't know. It just must be there or there. I mean, I don't care whether you put it there or there. I didn't know, when I do my wacky diagrams, I never know whether to put I didn't know whether to put the 2 there or there. Doesn't make any difference. Same with a half there. Same with k here. Let's put it there. And then the outer function up here must be what?
The outer function.
Or at least roughly, it must be roughly what? What's the integral of ke to the blob? With respect to blob, it's
k over blob.
Over? Are you confusing e with natural log or 1 over?
It's just e, isn't it?
It's just e to the power of. Yes. So we're nearly there. We just need to see if there's any adjustments needed. So how can we make this equal to that?
K is x divide by k.
If we divide by k, will that make the equal sign valid again? Does that make this equal sign true?
Well, you need to get rid of that first k. But
well, these would cancel actually. Yes, that's still not equal.
But then you'd get 3 over k on that side.
On which side? Here? This, we can't change that.
No,
that's given.
No, on with the 3x squared.
Right. Right. So should we backtrack a bit? Let's look at it again.
Yeah.
What adjustment do we need on the right-hand side so the equal sign is true?
Well, we need to get rid of that k on the left-hand side.
We can't get
on the left-hand side of our function. Yeah.
We want rid of that k. Doesn't it correspond to that k there?
Well, yeah, no, we just need to get rid of the 3. I was looking at the wrong route. Yeah.
Yeah.
What I was thinking is we were going to get rid of the k, and then the 3 was k.
Yeah, but we don't know that. 3 is 3 out of there. Whether that, maybe it'll end up being the k is 3, maybe. I don't know. But then you'd still need it here as well as there. So that is kind of irrelevant. You need a 3 in it on account of the x cubed.
Yeah. Okay.
So the adjustment we do need is what?
Is we need to get rid of the 3. Divide by 3.
Divide by 3.
Times a third.
Times a third is much better way of putting it, yeah. I'm half in, half out with my various multiples, but it's fine, isn't it?
Yeah.
Taking the limit. Oh, we'll make sure we just imagine integrating that. We would get a third k e to the thing times that. The 3's cancel, so we're back where we started there, which is fine.
Good.
So between 0 and k, what do we get?
We get third k e to the k cubed.
Yes. Good. Followed by
minus k e to the power of 0 cubed.
what happened to the third?
So 0, a third k. Oh, did you? I thought I said it.
Yeah, a third k e to the power of 0, or 0 cubed.
Isn't 0 cubed?
0. Sure.
Oh, no, that's, yeah, 0. Yes.
So of course this term simplifies to what?
1.
Right.
One.
The term.
Or no, k. A third. No, sorry. A third k. A third k.
Yeah.
Isn't it?
Yeah. So we can bring a third k out, which is probably what they've done. And inside we'll have what?
And inside we would have e k cubed,
E to the k cubed
minus 1.
Good. And now we use the information that that's got to be equal to 2/3 e to the 8 minus 1. Blimey. Perhaps I'll bring
where
that.
did you get equals 2/3 e8 minus 1. Okay, well, that means that we know that k is 2.
Oh, I'm not sure.
Yeah, it does.
2/3. I mean, all right, okay. I'm just saying I'm not sure. Hang on, let me catch up. E to the 8. Oh yeah, because you've checked it out with the k cubed. Pardon me. Yeah, that does solve it, doesn't it? K is 2. Yes, I mean, I was expecting to start balancing and unwrapping, but you've spotted k is 2. Cool. Next.
5.
Right. Okay, so again, we'll ignore the 4/5. We'll just do the integral and then use the extra information. We'll probably ignore the domain as well. Not sure.
Right, okay.
I mean, that's just saying if theta would be going further than 9 o'clock, perhaps it would get messy. I don't know. I don't think we have to worry about that. So from 0 to theta of 4 sine of 2x cos to the 4. Oh, I see. Just in terms of an unknown constant angle, but restricting the range of that constant, which is not a variable. It's confusing, I know, but right.
Yeah.
So how shall we pass 4 sine 2x times cos to the power 4 2x?
The inner function is.
So you're saying, I reckon there's a composite here with an inner and an outer, and the inner is, sorry to butt in.
And the inner would be 4 sine 2x.
No, bad luck. What would be the outer in that case? Try following that through. If the inner was sine,
sine.
what were you imagining the outer would be? timesing by something else, sure, but these outers, they're not usually just timesing by, are they? Because it just would need a different analysis in that case. So sorry, anyway, you're revising to what?
Oh yeah, but I was just, oh yeah. Okay, because I was thinking because sine differentiates to cos. That's why I was saying sine.
To be your inner derivative, fine. But then you maybe, if you follow that through, perhaps I'm trying to differentiate to cos to the power of 4. What on earth was the inner derivative if it differentiated to cos to the power of 4?
No, the outer function of that will be to the power of 4.
Well, exactly. Yeah. We can't do that one, can we? We've got to go back to saying the inner function here is what?
Cos 2x.
Exactly. And the outer function of that is power 4.
Yeah.
Good. So, up here?
Up there we'll have cos 2x to the power of 5 times a fifth.
Yes. And then down here? That will give us...
Down here we'll have minus sine 2x.
Careful. Notice there's another inner.
Oh, minus 2 sine 2x.
Minus 2 sine 2x is right. The inner derivative just has to be whatever it has to be.
Yeah.
Okay.
Okay. And then let's see, so we've got 4 cos 2x and we need to times it by minus 2.
Well done. In which case
the top becomes minus 2/5.
Yes. You're beginning to see it now without various unnecessary, well, for a start, you know, you're treating that as a multiple rather than dividing, which is good. Anyway, it's all good. You're just making the adjustments. You're seeing the big picture, and
yeah,
you know, the equal sign is true there, so we know we're done. So between 0 and theta, let's evaluate.
So minus 2/5 cos 2 times 2, so that's just going to be 0, isn't it?
No, I don't get you. Are you thinking of that as pi or something? I don't know.
Well, cos to the 0.
Oh, the second one. What is cos of 0?
Oh, I've got 0 on top for some reason. Okay.
Oh.
I just wrote it out wrong. Okay. So minus 2/5 cos 2 theta.
Well, don't forget power 5 of cos.
Oh yeah. Two theta, all minus.
So if x is 0, 2x obviously is 0. What's cos of 0? What time on the clock?
Uh, 3 o'clock.
And what the horizontal aspect of 3?
1.
Yes. So it's 1 that we're raising to the power 5.
Wait, minus 2/5, 1 to the power 5, isn't it?
Yes, and we're subtracting minus 2/5 times effectively 1.
Yeah. So just plus 2/5 essentially.
Yes, so we might as well put that first and this one second and call it, well, we could bring the 2/5 out actually, couldn't we? So 2/5 of 1 minus cos to the 5 of 2 theta.
Well, yeah. 2 theta, okay. And then that equals 4/5.
Ah, right, yes. And if that equals 4/5,
But then we can say
that gives us,
divide 4/5 by 2/5.
yes. Well, yes. I mean,
Which is
as long as, yeah.
20/10, so 2. 1 minus cos 5 2 theta equals 2.
Yes.
Cos 2. And then we could take 1, we could say cos 5 2 theta equals minus 1.
Yes, we can, can't we? Good. In which case, cos of 2
in which case cos,
so an odd power of a negative is,
an odd power of a negative is negative.
yes. So
yeah.
The root of an odd power is going to be negative. So cos 2 theta equals minus 1.
Yep.
And what time on the clock has a cos coordinate of minus 1?
Um, 9 o'clock.
In other words, in calculus?
In other words, minus 1.
No, but 9 o'clock is what angle in radians?
Oh, 180 degrees.
In radians.
And radians, pi.
Yeah. And so now we see
So
what they were reassuring us that we only need consider, you know, we don't have to halve 2 pi as well or anything, or 3 pi, because we only want final answers between 0 and pi. And our final answer is pi over 2. Okay,
good.
Next.
Do 6.
Yeah, have I got that? Yeah, kind of. Yeah, I'm sure it's all there.
Okay, by equal.
That was all of it. Good. Right. So part A, find the integral of cot x by writing it as cos over sine.
Okay. So that's find integral of, okay, which equals cos x sine x to the minus 1.
Yes.
And then
So inner and outer
we
and
can,
derivative.
yeah. So the inner is likely going to be so if it was, it's probably sine x, isn't it?
Yeah, yes, sorry. Absolutely.
Yeah.
Good.
Sine x, and then so that on the outer it will be to the minus 1.
Yeah.
And then the other blob will be
Yeah.
cos x.
Get into the habit of not, skirt that issue because it should come out in the wash. I mean, you're hoping it's going to be
Oh,
all of that. I'm not,
yeah.
what you're
Well,
saying is not wrong.
yeah.
I'm just saying, yeah, fine. But that will also
It'll be ln x,
be cos x
ln
because,
sine x.
yeah. But even before deciding ln, you could be putting the sine x there and then you could put that. No, I'm, I'm interfering unnecessarily here. Anyway, that's all correct, isn't it, basically? No adjustments needed. Would be. But of course, oh no, that's all there is to it. Yeah. Natural log of sine. No, hang on a minute. Yeah, all right.
It is only 2 marks.
Yeah, it just looks unfamiliar. Natural log of sine. So obviously it's going to be 1 over sine times cos. Okay, all right. Just looked unfamiliar, that's all. Right. Show that the integral by doing similarly, basically. So part A is just a hint of how to go about integrating tan. They're saying, look at cot. It turns out very nicely. Try and do tan, even though you'll find it's not quite as neat, or there's a bit more to it. But do it in the same way as you did cot.
Okay, so tan, find the tan. Okay, well, tan x equals sine x over cos x.
Yeah.
Which equals sine x times cos x to the minus 1. And then we can say that with the inner function of cos x,
Yeah, that's right.
an outer function minus 1,
Yeah.
then so that's gonna integrate to ln
Yeah.
cos x,
Good.
and then that's gonna shoot out minus sine x.
Exactly. Good. Yes, that has to be whatever it has to be. Good.
And
In which case?
and then in which case we will times it by minus 1.
Yes. In which case?
In which case ln sec x plus c.
Oh, don't cheat.
Oh.
You told me to put a minus here, although you might have meant also putting a minus where?
On top, on top.
Yeah, which hopefully you did mean. Put that
Yeah.
minus in on top. And now perhaps cheat and think, well, am I done here if I put a plus C? Well, it's not quite what they've got. Why not?
Because they've got ln sec, so ln 1 over cos x.
Remember what we said about this here. You see what I wanted naturally to do with that half, if I could, if it was useful. Put it there.
Yeah.
Well, that goes for any multiple.
Okay, so now we'll
minus 1.
Yeah. Yeah, okay.
So we should rewrite
ln
that
cos
as ln of
minus 1x
cos
ln,
cos x to the minus 1, yeah?
yeah.
Which of course means what? What's cos x to the minus 1?
Ln sec x.
Well, yes, because
Or
power minus 1 here doesn't mean reverse cos, it means 1 over, doesn't it?
Yeah.
So it's 1 over cos, which of course is log sec.
Good.
Which is how we usually state it. Okay. Next.
Okay. I don't know. The ones I had for 11. Let me just see what I wrote down. 11e. What was it? 2c.
Right.
This is now substitution.
Okay. Sorry, 2e, did you say?
2c.
2c, fine. Now, the other day I was saying, you know, I was trying not to be too dogmatic, and I was saying, you know, well, actually they're telling you to use a substitution, so you must. Well, it's true, you must. But
okay, well.
Anyway, right.
Oh.
Well, yeah. So tell me what you're getting for this.
Well, it tells, so I differentiate the u.
Yes. Do you, with respect to?
Dx.
Yeah. And du dx then equals?
So dx will then equal.
Oh, sorry, did I miss your
1
answer?
over minus.
Yes. Okay.
Minus sign x.
Yeah, exactly.
And then dx will equal du over minus sine x minus du over sine x.
Yeah, quite. So you could call it minus cosec x. Maybe I'm being a bit, maybe there was no need for that.
How can you say that if we don't know what du is?
Du, don't forget, is just going to be a closing bracket. That's what.
Yeah, no. How could you just call that 1? Like, how could you assume it was 1? I know we do just get rid of it in the end, but like at this stage, how did you know you could just call it cosec as if it was 1?
Well, let's go from your version, which was du over minus sine x. All I'm doing is rewriting that as du times minus 1 over sine x, or du times minus cosec x.
Okay. Oh, I see. Yeah.
Okay.
And then so what do we do next? We put the du over minus du over sine x in the equation.
Well, that's right. There's nothing more needed really. We can go right ahead now and say that equals, oh, sorry, what we ought to do is say x equals pi over 2 gives us u equals, and similarly here, x equals 0 gives us a u limit of, so in each case, if x is pi over 2, what's u?
If x is pi over 2,
which is what time?
u would be pi over 2 is 12 o'clock, so 0.
So 0, good. And if x is 0, u would be?
U will be 1.
Yeah. As I was saying before, you could be ruthless and substitute for every single thing in here. But with practice, you don't really want to bother. You just let's go ahead and substitute now. So the integral between those limits. Now we do want to switch those round. And by the way, you might prefer to switch them around straight away and write this instead, from 0 up to 1, but the negative. You could put the negative outside the integral, so that's not interfering.
Why straight away?
Well, no, exactly. We could leave it for a later step and leave it as that for now. But of course, before we get going on evaluating an integral, we just prefer to have lower to higher there.
Yeah.
And because you are thinking of it in the back of your mind as subtracting an earlier cumulative area from a later cumulative area, it does make sense to think of the top area as larger than the bottom area. Now, I haven't talked about that for several weeks, but in general, when you get the area between two limits here and here, what you're really doing is subtracting the cumulative area up to this point since forever, since minus infinity on the x-axis. You're subtracting that one from the larger one to get this difference, which is why we like to put the earlier x value here and the later x value there.
Okay. Yeah, okay.
But we don't have to do it immediately. We can leave that kind of the wrong way round for now. And then we've got, well, let's leave sine x alone because we've got a hunch it's going to get taken care of in a minute, times square root of what?
Times the square root of 3u plus 1.
Yeah. And dx is going to become?
And it's going to become d minus du over sine x.
All right, but let's leave the du till last, if you don't mind. Let's write it as minus times minus cosec x du, and then we've got the closing du as a closing bracket. But actually, I'm being really that's a matter of, you know, there was no need for me to change those around actually. But I have changed them around, and now I've got du as the closing bracket. So, and we can see that sine is cancelling the cosec, which is be clearer your way if you write it as sine here and 1 over sine there. We have got a minus here though. So do you see the effect of that is actually going to be what then? How is it simplifying?
I was a bit confused about what you were saying about the sine x.
Well, that might be my fault for calling it cosec over here rather than 1 over sine. But since this cosec is really 1 over sine, it's cancelling this sine here, isn't it?
Oh yeah, we can just cancel them. Yeah, so we just cancel the sine and the du.
Yeah.
Cosec.
Well, yeah. Not du, but the cosec. Yeah, yeah. So what are we left with?
Root 3u plus 1.
Carry on.
Du.
Not quite. One important detail here.
Minus du.
At least. Yes. And bear in mind, that doesn't mean minus du. It means times minus 1. And then all of it closed off with a du.
Right. Okay.
So what we've really got is the integral of minus the square root of that with respect to u.
Yeah, okay. Yep.
And then what?
And then we differentiate. No, not differentiate. We integrate it.
Not yet, because we've still got these rather anomalous limits. We've got the later x value here. Don't forget, we're going to be subtracting this result from that result. So we would rather write it as minus the integral from 0 up to 1.
All right, okay.
But if we do that, we've got this, haven't we?
So we could say 3u minus 3u plus 1 to the minus 1. No, to the half, sorry.
Well, we could say power of a half instead of a square root sign, but what this really cries out for is what? Simplification. I mean, if you've got minus the integral of
getting rid of the minuses.
These surely cancel, don't they? Those two minuses just cancel.
Yeah, you get rid of the minuses. Yeah.
And then, yes, let's write power of a half rather than square root sign. That is a point.
And then we can integrate it.
Yeah. And what do we get?
Okay, so that will be that'll be 3 over 2 times 2 over 3 times 3 plus 1, 3 over 2.
Right. But if we test that, so the inner function is, you're right, that will be that same inner function all to the power of 3/2 and therefore 2/3. But
then we divide by 3.
We'll need to, because the inner function is differentiates to 3. That's right.
Yeah.
So our integral in the end is what?
one, well, yeah, our integral is 2/9
That's it.
3u plus 1.
Yes, quite. 2/9 of that to the power of 3/2. Good. From 0 to 1. Giving?
Giving 2/9 3 cos x plus 1.
Did you say cos? Oh,
Yeah, the u is equal.
I mean, there's no need, by the way. If you've changed the limits in terms of u, you don't have to substitute back. Although you can, if you like. You should get the same results. The limits haven't really changed at all. Really, it's just that.
So we don't.
I mean, if we're substituting for u here, then we use the 1. If we're substituting for cos x, which is what u refers to, sure, then we would need the previous limit of whatever it was. We'd have to be careful because we switched them around now, but you know, here.
Yeah.
But you know, a u value of 1 corresponded to an x value of 0, actually, didn't it? Yes. I think I was
an x
using those. So anyway,
0.
So just using u, because you can, the first evaluation.
So then we know that u is basically 0. When u is 0, then we can say 2/9 times 1.
That's right. And what about the first evaluation? What do we get for plugging 1 into u?
2/9 times 1, because 3u comes to 0, plus 1 to the 3/2 is 1, so 2/9.
Sorry, which one are you doing? Are you doing this limit or that limit?
The first one, 1.
1, okay.
When u equals 1, cos x comes to 0.
You're doing cos again. Are you doing it in terms of u or x?
Yeah.
You see, our antiderivative here, our indefinite integral inside the square brackets, is in terms of u now. That's why we changed the limits, so that we didn't have to worry about those angles anymore. We've done the consulting the unit circle or whatever. All we have to do now is say our u value, when our u value is 1, because cos x is 0, yeah. But with a u value of 1, we just get 2/9 times what to the power of 3/2?
Times
u is 1?
4.
Which to the power of 3/2 is? 4 to the power of 3/2 is?
4 to the power of 3/2 is 6.
You surprised me because you picked me up a couple of minutes ago on a similar mistake I was making. I thought 4 to the power of 3/2 as, yes, that's what we're doing. Aren't you square rooting and then cubing? Did you halve and then triple?
Oh yeah.
Or square root and then triple?
Yeah, 8, sorry.
8, yeah.
Minus
the 0 version, where it's what to the power of 3/2?
Where it is 1 to the 3/2, so just 1.
So just 1. So we get
2/9 to the 7 times 7, which is 14/9.
Good. And then was there an extra bit? No. I just wanted an answer, which is 14/9.
Good.
I was just looking at it. We did it as a u substitution because it said u equals cos x, and
Yeah.
presumably it implied please use that, and we might as well anyway. But did we recognise how? Hang on a sec. Did we recognise how it was a perfectly good case for doing it by inspection in preference to substitution as well, which does often happen. If they give you a substitution to use,
Yeah.
it still might be worth looking at it by inspection as well.
When you say by inspection, do you mean reverse chain rule?
Yes, I mean, if you look at sine x times that square root,
Mm.
how does it pass as a reverse chain rule? Yeah. I mean, let's just note that. What was it? Sine x times square root of 3 cos x plus 1?
Yeah, something like that.
It would just be a shame not to recognize how it is a composite times something else. Tell me the composite.
Hold on, I've lost you.
Oh, have you lost?
No, just the image has just come off for a second. I just clicked. Okay, cool. I've got you right now. So
The
the
reverse chain rule, how does it fit that lower level of the chain rule?
wouldn't it be 3 cos x plus 1 to the half in the?
Exactly. Good. And then this would have to be what?
That would have to be that would have to be 3 sine x
Careful.
minus 3 sine x.
Minus 3 sine x. Good. In which case, the whole thing. So they're equal.
So they're equal. We would times it by minus a third.
Good. And then up here we'd have
Minus a third, 3 cos x plus 1 to the half.
would we? Are you sure?
Oh, no. We'd have, sorry, 3 cos x plus 1 to the 3 over 2.
And therefore?
And therefore we divide by 3 over 2, so we times by 2 over 3. So we'd have 2 over 6, which is the same as 2 1/3.
It's not 2 over 6, is it? Careful.
Oh, 3 over 6. No, yeah, 2
What are you
times 1
multiplying this by?
by 2 over 3.
Yes. What's a third times 2/3?
Oh, yeah, of course. Okay, it would be 2 over 9.
Yeah.
Yeah.
And then we can check that. So 3 halves times minus 2 over 9 is minus a third times that to the reduced power. All times that, and then they cancel. And we should have what we had earlier. But this time the limits will be what they were given as. Which was 0 to pi over 2. So this time we're not going to bother changing the limits. But this was from 0 to pi over 2 of that stuff. All with respect to x. And so If x is pi over 2, what's cos x?
That would be cos 90, so 0.
Good. Plus 1 makes
1.
To the power of 3/2 is still
Still 1.
times minus 2/9 is
Minus 2/9 is 1. It's just minus 2/9.
yeah.
Yeah.
Because that was 1. That's what we were doing, isn't it? And then
Yeah.
minus the 0 version. Well, if x is 0, cos x is
1.
yes. Times 3 is
3.
plus 1 is
4
to the power of 3/2
is would be, let me think, that would be 2 cubed is 8.
good. Times minus 2/9 is
Times minus 2/9 would be minus 16 over 9.
good. And we were subtracting that negative 16 over 9, weren't we?
Yeah.
So in the end, we get
So in the end, we get 14 over 9.
which is indeed
What we got?
same.
Good.
So even though, it might be a good enough example for doing a U substitution, it's just not an example where the U substitution was really called for. Anyway,
Yeah.
right, where next?